Hi guys, let's look at the solubility portion of this handout. When we're considering solubility, we have an old adage, and that is that like dissolves like. This means that a compound or a solute, I'll typically call it a compound, will dissolve best in a solvent that has similar physical properties, more specifically similar IMFs. And the more IMFs that can be formed between a compound and a solvent, the more soluble the compound will be. What type of IMFs are we talking about? Well, we've covered those. And we looked at 4 different types of IMFs. They're listed over here in order of strength or importance, ionic being the strongest. Note with our IMFs that these are also types of polarity. And thus an ionic attraction or a compound that is ionic is going to be called or considered the most polar. A compound or solvent that is able to do hydrogen bonding is going to be considered more polar than one that can only do, for example, van der Waals, have van der Waals attractions induced. So this is also a degree of polarity in our discussion. Thus, when we say like dissolves like, do they have comparable polarities? Question: which carboxamide or amide above will be most soluble in water? Well, water is considered a very polar solvent. Now, it's actually a polar molecule. It has a molecular dipole moment. But in terms of the IMFs, we call it polar because it can participate in lots of hydrogen bonding. Now, it's not ionic, but it does have hydrogen bonding potential. Hexane, on the other hand, which is the next question, is just a hydrocarbon. A saturated hydrocarbon cannot do hydrogen bonding. It can only participate in van der Waals attraction or London forces, that weak induced dipole stuff. Okay, so we got a polar solvent, and we call this nonpolar because, again, if we look at the IMFs, polar would be more of 3 and 4, less polar would be more like 1, and 1 we would essentially say fairly non-polar, the opposite of highly polar. So that's using the terminology. Okay, so which amide above will be most soluble in water? It would be the primary amide because more hydrogen bonding possible here. We could envision the O. We could even just count acceptors and donors. I mean, this compound has the oxygen could be an acceptor. The nitrogen could arguably be an acceptor. Now, the lone pair is in a p orbital, but it's possible that it's an acceptor. And then it's got 2 donors. While this compound over here only has 2 acceptors and there's no donors, so it has less hydrogen bonding potential. Water has a lot of hydrogen bonding potential. Of the 2 up here, this amide does as well, and so these 2 are more alike. And like solvent will dissolve a like compound. So I would expect the primary amide to be more soluble in water. On the other hand, the tertiary amide with less hydrogen bonding is going to be more soluble in the hydrocarbon solvent, which has, well, no hydrogen bonding. So they're more alike in that regard. We can also look at this another way. in terms of solubility. These compounds are solids, and most of the time when you're looking to dissolve something, it's probably going to be a solid. And we've got that solvent has to get in there and break these molecules apart, the different molecules. We're not breaking covalent bonds when we dissolve, but we are breaking some of the IMFs. And we have to establish new IMFs with the solvent. Well, which of these molecules are going to be stuck together more? The primary amide. Lots more hydrogen bonding possible between one amide and another. And that's why the melting point is high. More IMFs here than here. Because there's more IMFs here, it's going to be more difficult for a solvent to separate the individual molecules from each other, which has to occur during the dissolving process. Hexane is going to have a tough time separating these molecules. These molecules are not going to want to form strong IMFs to hexane. They can't. But the molecules can form strong IMFs to water, hydrogen bonding IMFs. So water is going to have an easier time separating these molecules and establishing new IMFs. In the end, we get back to like dissolves like. Okay. Just trying to give you some discussion here of how to judge solubility. We'll see other examples, including in this handout. Okay, at this point, I want to introduce you to some common solvents in the lab. First off, we have water versus organic solvents. Of course, organic solvents are carbon-containing solvents. Number of organic solvents. I give you some here. I separate these into polar and non-polar. Have to be careful though. The only one over here that's truly non-polar is hexane. And maybe toluene. In fact, I would say probably toluene if you, based on what we said before. But diethyl ether and ethyl acetate are actually polar molecules. Because if you assess individual dipoles and then consider a molecular dipole moment, you'll see that these do have a dipole. So why do I consider them nonpolar? The reason is because these over here on the right are all insoluble in water. They don't mix with water. And that's why I'm calling them non-polar. You see, diethyl ether, even though it's a polar solvent per se, it's not polar enough to mix with water. Neither is ethyl acetate. Neither is dichloromethane, which is actually a polar molecule. So, we have to understand the difference between a strict assessment of polarity versus more of a working definition of polarity. And when we say a compound is polar, there's a continuum there. It could be slightly polar, which these are, or it can be sort of strongly polar. Now these on the left are all soluble in water, and so that's why I'm calling them polar solvents. And indeed the molecules are all themselves actually formally polar molecules. Now terminology. A compound that really likes water here, these are called hydrophilic, right? Water loving. Or these over here that do not mix with water, these are going to be called hydrophobic, water-hating. Or we could call these lipophilic, with lipid or lipo here referring to sort of fat-like. And fat-like being considered non-polar. So these terms you need to know and be able to use them, and you've probably seen them in Gen Chem. Okay. Now, in terms of the names of these actual solvents, you do not have to sort of memorize these. These are sort of just a reference listing of them. We will see these in lab. Our very first lab, solubility lab, we use hexane. Ethyl acetate, yeah. Acetone we use to wash our glassware. Okay, it does mix fully with water. If you mix these with water, there will only be one layer because they completely mix. They're miscible. If you try to mix these with water, you'll have two layers. At that point, you need to know density. Less dense solvents will sit on top of the water. More dense solvents will sit on bottom, or would be the lower layer. Now, these solvents over here are useful for extracting aqueous solutions. When we talk about that, we will see that you need two layers, an aqueous layer and then an organic layer. If you need two layers, you've got to use one of these solvents here that doesn't mix with water. You can't do an extraction with like acetone, because if you add acetone with an aqueous layer, you will not have two layers. It'll mix and you'll just have one layer. Same for any of these other solvents. Ethanol you're familiar with, alcohol, common alcohol. Acetic acid, it's actually a fairly good solvent, common solvent. It's a weak acid, but it can be used as a solvent. DMSO and DMF are considered polar aprotic solvents because they don't have a proton that can participate in hydrogen bonding. Acetone is also a polar aprotic. Ethanol and acetic acid are considered protic. The protic term is referring to the fact that it has an H there that can participate in hydrogen bonding. Or it can do other chemistry. It's acidic enough to do some chemistry where the H's on these other compounds can't do hydrogen bonding, and they're less likely to do acid-base chemistry. DMF stands for dimethylformamide. DMSO is commonly used for NMR as an NMR solvent. You'll see that in organic 2. Note that DMSO is very similar to acetone, except the carbon has been replaced with sulfur. The sulfur does have a lone pair. You should know that, right? Okay. We do have an aromatic solvent here, toluene. If you take off the methyl, that's benzene. Benzene is a good solvent. Unfortunately, it's quite toxic. The methyl group on it's less toxic, and toluene is a common aromatic solvent. So we see different functional groups here, hydrocarbons, ether, ester, ketone, even an amide. Most amides are solids with larger R groups, but with an H here, it's actually a liquid. Okay. So there's many things we could say about solvents. This is just sort of an intro and some sort of introductory discussion there. One last thing before I turn the page here, we do have a halogenated solvent. It's a common term. There are a few common halogenated solvents like dichloromethane, or you may have heard of chloroform, which is not here, but that's another common one. Okay. Water. Is water good for anything? Well, water is not great for organics, especially neutral organics. Not good. It's really not the universal solvent. But water is good for most organic salts. Okay? Salt meaning ion pairs. It will dissolve some highly polar neutral organics. Neutral in this case meaning non-charged, such as sugar. Okay, if you look at sugar molecule, sucrose, it is not charged, so it's not ionic, it's not a salt, but it is highly polar because it has several OH groups, and those OH groups can participate in hydrogen bonding with water. And so in that regard, they're similar, and we get back to the adage, like dissolves like. But sugar doesn't dissolve easily in water. You have to usually heat the water, right? If you're dissolving sugar in your kitchen. Okay. But water does dissolve most organic salts. Or is there an exception to that? Yes, there's a couple of notable exceptions. This salt, this ionic compound, actually is not that soluble in water. This is calcium oxalate. It is organic. It has 2 carbons. And this will actually precipitate in your kidneys because the solubility is quite low. And so it does not stay dissolved readily. And it forms precipitates in the kidneys, and we call that kidney stones. Okay, because the compound is in your body, but it's not highly soluble, and it tends to separate if the concentration becomes high. Another example of a ionic compound that is not highly soluble in water is sodium urate. It's the sodium salt of uric acid. And it will, if it gets too concentrated in your body, it will form a precipitate in your joints. And when this starts to happen, we call the condition gout, which you may have heard of. If not, you can look it up on the Wikipedia. All right. But we generally say that water will dissolve most ionics. As with most everything we say, there are exceptions. Okay, polar organics versus non-polar organics. I give you just a little bit of description of what these are good for. All right, should be pretty straightforward. You can read that yourself. I mentioned extraction. And we can take a look at this down here. We'll probably look back at this once we do more acid-base chemistry, but let me take you through an extraction process as shown. Extraction is a good way to separate compounds. Here we have 2 compounds in the box. One of them is a carboxylic acid. Okay. One of them is an alcohol. By the way, the carboxylic acid functional group is condensed here. All right. It's not showing full structure. Of course, full structure is carbon double bond OH. Here it's just showed as COOH. Because sometimes things are done like this because it's just easier to type if you're typing. You may also see this as CO2H. All right, but carboxylic acid. These can be separated by an extraction process. We can dissolve them both in an organic solvent such as dichloromethane. All right. Neutral organics dissolve in a neutral organic solvent. All right. Then we can add in a base, like 10% sodium hydroxide solution, 10% aqueous solution. So now we have water, basic water. These will not mix. They'll form two layers. At this point, the two compounds have a choice of which layer they will move into. And why did we add base? Because a carboxylic acid is acidic, and a base will deprotonate the carboxylic acid and convert it to the sodium salt, which is ionic. All right. But the alcohol will remain neutral. All right, just to clarify that. Because sodium hydroxide is not strong enough of a base to deprotonate the alcohol. Now, how do we know that? Because the pKa of a carboxylic acid is about 4. Where did we first mention that? Well, the acid-base handout, one of the first pages. And the pK of an alcohol is what? Is about 16. Okay? And the pKa of sodium hydroxide is, well, about 16. What do we mean by pKa? I thought that described an acid. Well, we need to understand how we use pKa's for bases. Knowing these numbers, you should know that the acid-base reaction will take place with the carboxylic acid, and it will be converted to the ion, but not the alcohol. Now, back to solubility. Ionic compounds prefer water. Neutral organics prefer neutral organic solvents. And so if we shake this up and allow it to partition, and that's just a fancy word for separate, we're dividing these into parts. Okay, partitioning. One of these compounds will go in the water layer preferentially and the other in the dichloromethane. At this point, we can just separate the layers. Drain one layer into one flask, another in the other, and now you have separated the compounds by an extraction process, an acid-base extraction process. Now, how can we get the compounds back? We need to get rid of the solvent. The dichloromethane can just be evaporated out, and the non-volatile organic compound will remain in the flask. And that's one characteristics of solvents. We typically want them to have low boiling points so we can evaporate them readily. And the boiling point of dichloromethane is about 40 degrees Celsius. Pretty low, easy to evaporate. All right. Now, in the water layer, we have the ionic form of our carboxylic acid, the sodium salt. We can get it back, but we need to put the proton back on. We can treat this with our favorite strong acids, such as maybe HCl. And the acid-base reaction will take place. And the carboxylic acid will go back to the neutral form, and this may form a precipitate here. And if it forms a precipitate, we can then filter it off. And that would be one way to isolate our product. That is, to get them away from the solvent, to get them out of solution. Okay. You can read, I'm sure these, trying to give you some important information here. I've given you the overview here, I think, and in the end, understanding an acid-base extraction is important. And ultimately, if we take it back to solubility, we're creating a scenario where we have hugely different solubilities of two compounds here, and we're using that difference in solubility to separate them. Because we have a scenario where we have two different layers, because we've chosen a solvent that is not soluble in water, that will give us two layers when mixed with water. All right. Now this diagram here is showing the non-covalent interactions. Okay, let's remember the NCI. Non-covalent interactions between a drug, Crestor, which if you watch TV, you've probably seen. It's a drug used to treat high cholesterol. This drug works by binding to an enzyme called HMG-CoA reductase, and this is showing the drug within the sort of binding pocket. The enzyme is all around, and typically drugs sort of fit into the enzyme like a key fitting into a lock, and we call that the pocket of the enzyme. Well, guess why will a drug do this? Because there's certain IMFs that take place in the pocket. What type of IMFs are taking place here? Well, let's take a look. We got to be careful too. Let's look over here. This looks like a hydrogen bond between the oxygen and first off, what is this over here? These are amino acids, because an enzyme is a protein, and a protein is made up of amino acids, and so that's the enzyme, and then the drug is forming IMFs with each individual amino acid in the enzyme. Hydrogen bond here, okay. You got to be a little bit careful and make this a little bit more specific. There's a lone pair here, right? And it's forming a NCI with the H that's on a nitrogen. These are F lone pairs. Hydrogen bonding to an H that's on a nitrogen, yeah. But I say careful down here, because here the serine amino acid, which you may have learned some amino acids in biology courses, this is serine. And we know it has the CH2OH side group, okay? But that OH can hydrogen bond. But look at this. This looks like two oxygens hydrogen bonding. I don't know who drew this, but they need to retake organic chemistry. This should have been shown to the H, right? Because two H bond acceptors do not form an NCI. Also up here, two H's, okay? So you got to recognize there's some problems with this drawing. Now Now here is kind of ionic because this is an ion, this is minus, okay, it's anion, this is plus. So you could call this an ionic attraction, but it's also sort of like hydrogen bonding if we consider that there's 3 lone pairs here and you got an H on a nitrogen. But since ionic is a stronger type of IMF, let's call it ionic. Okay. Yeah, I mean, just make sure you see the problems with the way this is presented. But let's go back to what it is correctly showing. This is showing how a drug fits into an enzyme pocket by forming different types of IMFs with the enzyme. Now we can also have drug design here. Drug design. For example, why do you think that this OH was put here in the drug? The molecule was created with an OH here, so when it moves into the enzyme pocket, it can form nice hydrogen bonds with the amino acids here, like glutamate or aspartate or lysine. Okay, if that OH was not there, there would be less IMFs between the drug and the enzyme. All right, so drugs are designed in this way, and it starts by knowing sort of the structure and what does the enzyme pocket look like. Then we can more rationally design a drug to strongly fit into that enzyme pocket. Last thing here, what are hydrophobic bonds? This is another way to refer to van der Waals attractions. And compounds that do van der Waals attractions are typically going to be just hydrocarbons. Well, or because that's all they can do, we sort of refer to van der Waals when we talk about hydrocarbons. So, look right here in this drug. It has this group, and later if you watch nomenclature, we call that an isopropyl group, right? What type of IMF can an isopropyl group participate in? Well, only van der Waals attractions. So what type of amino acid side chain would it want to interact with? Sort of just hydrocarbon. It's not going to want to interact with a polar side chain. It has no way to. Well, it turns out if you know your amino acids, all of these amino acids here have alkyl side chains. Okay? For example, a isobutyl group coming off of one of them, like I think leucine or valine. I haven't looked at those in a long time, but if we got these hydrocarbon groups coming off, these can form, okay, an NCI, a non-covalent interaction, in what we call van der Waals attractions. And that's probably why the isopropyl group was put there. Now that's a weak interaction, but it's better than nothing, right? Okay. Let's look at soap here. How does a soap work? How does a soap clean your body or when you wash your hair? we typically bathe in water, right? Not acetone or ethyl acetate, water. And so how do we get the oils? Oils are typically lipophilic. Well, a soap has sort of two portions. It has an ionic end, all right? And that's going to be the hydrophilic portion, all right? That means it likes water. This end likes water. But it also has a long hydrocarbon chain, nonpolar. And this is going to like oils. Okay? Oils are typically regarded as fat-like and nonpolar. But oils that accumulate in our hair and on our skin, or this is typically when we bathe, we're removing oils and dirt, but dirt is more of a, we remove that more mechanically. We don't dissolve it. But a soap can do this because it mixes with the water that's coming out of your shower or in your bath. But it also is willing to mix with those oils, and it helps pull the two together and sort of then washes everything down the drain. Now, there's more to it than that. It's actually known that the hydrocarbon chain will associate around an oil droplet, or in this diagram, grease, and then the polar groups will be sticking outward, and they can associate with water, maybe through some hydrogen bonding, you know, all the way around, and we can get that grease washed off in this manner. So the anatomy of a soap and understanding some terms and how this might work. Hydrophilic versus hydrophobic portions. Okay, question over here. Here are two drugs used to treat gastric reflux. Prilosec and Nexium. You've probably heard of these. One of them is a neutral compound, no charge. The other one is the magnesium salt. Question here, and it should be a very simple question. Which of these would be more soluble in water? Well, the answer is pretty straightforward. It would be Nexium because it's ionic, right? Ionics are typically more soluble in water. Did you know that that was the only difference between the two? Prilosec came out originally, and then Nexium came out. But guess what? If you put this in the stomach, which consists of HCl, it's going to be converted to, well, Prilosec. So once these are dissolved, they're the same in the same location. If they're both in the stomach, they're both going to exist with the proton on. And in the acid-base handout, we'll talk about proton on versus proton off. So they're the same once they hit the stomach, or they're the same in the bloodstream. The difference is Nexium will cost you a lot more money. Now, why was the drug company able to get a new patent on the salt versus the neutral? Probably because Nexium will dissolve faster when it goes to the stomach. Because it's ionic, it will dissolve faster than the neutral compound. That's probably the difference. But once they're dissolved, they're the same. Okay. In this example, I show you a herbicide, dicamba. This would be the neutral compound. But herbicides are typically going to be dissolved in water and then applied as a solution or as a spray. Well, this compound doesn't dissolve readily in water, it turns out. How can we make it more water soluble? We can convert the carboxyl group to a salt, the sodium salt. more soluble in water. And now we can more readily make a solution in your garden to spray this or in the soybean field. The problem is this sodium salt is hygroscopic. All right. We can read that definition here, but it will absorb water from the atmosphere and it'll become sticky. And that makes it not a good solid. I mean, if you pull some out of a bag and try to dissolve it, if it's all like sticky and clumpy, it's just not good to handle. And so this agricultural company has did research to develop other salts instead of sodium. We could say, well, what about potassium salt or lithium salt? I'm not sure about those, but others that have been developed are ones that have an organic cation. Okay, the cation portion is organic. The first one was the DMA salt, and these are not as hygroscopic. Now that's hard to predict, but I think that's the case here. Now, well, we could possibly say why they're less hygroscopic. They're more carbon, and hydrocarbon is typically going to be less hydrophilic. But another problem with some of these herbicides is volatility. And you can read about this, but they're getting in the atmosphere because of volatility, and they're moving to other fields and killing crops. And what they've done here is they've increased the size of the organic cation to make it less volatile. All right. They've also added hydrogen bonding. All three of these are cations, but these have H bonding in the cation, and this reduces the boiling point / volatility / vapor pressure. Any word would work. Probably vapor pressure is the first word you would use. More IMFs is going to lower the vapor pressure, and thus there's going to be less compound in the vapor, and thus it's not going to evaporate as much. And move in the air as much, and maybe get blown over to a nearby field. Okay, this is sort of complex, but it's worth reading. It takes a little time to explain it all. Hopefully there's enough here. There are some important words such as hygroscopic, understanding organic cations here versus just metal cations or non-organic cations. And just thinking about the application and what type of research went into developing these new salts. Okay. The last page in this handout is a very nice picture here, and I've got it in color, so I'm going to show that. This compound up here has R groups. Now R groups have to be defined. There's no R in the periodic table. These are defined below. When both R groups are methyl groups, okay, the compound is called methyl red. Red because as a solid it's red, but when you dissolve it, it's yellow. And this is showing the compound in a biphasic mixture of cyclohexane and water. Of course, cyclohexane is a hydrocarbon, but it's a ring, so it's a cyclic hydrocarbon. It does not mix with water, so we get two phases. And you can shake this up and partition it, but it turns out that when the compound has methyl groups, it's going to highly prefer the water, and we can see that by the color. If you change the groups to ethyl groups, the compound now starts to prefer the organic layer. A little bit in the water. If we go to propyl groups, we see that it highly prefers the organic layer. All right. Important thing is the trend, and does it make sense? And the answer is yes. And this is a very important point if we haven't made it previously. The more hydrocarbon you have in a compound or a solvent or any molecule, the more hydrocarbon you have, the more it's going to prefer an organic solvent. We can also say this: the more hydrocarbon you have, the more lipophilic. Okay? If we come this way, we get more lipophilic. Because hydrocarbon is known to be lipid-like. Lipid-like meaning very nonpolar. Now, to me, this is a very drastic change. You know, these are almost like, what's the big difference? It's not like this is 1 carbon and this is 10. We're just going from 1 to 2. But the extra carbon is changing the solubility properties of this molecule. Now, it's actually 2 because we got 2 methyls. And when you go to each ethyl, this molecule has 2 more carbons than this one. So it's sort of double because we got 2 groups here. It's a very drastic change, though. But this is important. More hydrocarbon, more lipophilic. Okay. I'll let you look at the one below on your own. Pretty straightforward. And the question, as I say, should be pretty easy, hopefully. All right. This also introduces you to some radio contrasting agents and a reason why solubility is important in the body. When considering which agent is best to use, which may have more side effects, etc. So, in the end, I give you a couple of sort of applications so we can make the information relevant to us. And moving forward, when you get out in the real world, you need to be able to apply your textbook knowledge to real world applications, either in some non-medical industry that uses organic chemistry, or some very medically related industry or topic, such as drugs or contrasting agents, etc. Okay, guys, that's an overview from me on solubility. We'll see what type of questions have come up from that, and see you soon.